Welcome back to the part 2 of this ripple carry adder, 4-bit triple carry adder using 1-bit full adder. So theory part we already discussed. So let's do the coding now. So as I said earlier, this model sim Intel FPGA, this icon, you have to double click. So once you double click, so this is what you see. So as I told, you can go with this jump start and then create project. Then this wizard is what we also get from here, file. So let's close this approach and let's go to this file and then new and then project. So this will prompt here that already one existing project is open. Want to close that? Yes, we want to close that existing. Then you will see this dialog box. So here you just type RCA 4-bit. So again, those rules are applicable that earlier I discussed. Do not give any space like RCA space 4 space bit like that. So no spaces. Spaces are not allowed. So do not give any spaces. Now coming to this project location, this is also important. Browse. And then in the lab demos here, I'm creating a folder, new folder. And then I'm giving folder name here RCA 4-bit. RCA 4-bit. So select that folder. And then click on this select folder. So with this two done, do not touch the other two here. Leave them default, whatever they are. Then click OK. Now, this prompt, we can close. We can go here, file. It is again the same, like the way that just now what we have closed. So here, but here directly, like when you go to the file, new, and then source here, this Verilog file, if you choose, then directly a file will open here, wherein you have to start coding. So as I said, if you are recollecting the part 1 video, in that we have discussed that this ripple carry adder means we have inside this 4-bit ripple carry adder, 4 1-bit full adders are there. We are remembering that 4 1-bit full adders are there. These full adders are what going to get this bits like A of 0. And this is going to get B of 0. And this is going to get A of 1. This is going to get B of 1. And the carry of this stage is fed to this stage. So this one we already seen in part 1 of this RCA ripple carry adder discussion, which is recording is available. Okay. So now we are going to do the coding. So here what is required, if you look at this one, we only require 1-bit full adder. And we have to connect them in a proper way, that's all. So let's do 1-bit full adder coding first. So here, this is full adder FA, module FA. This FA has got 3 inputs, A, comma, B, comma, C in. And it has got 2 outputs, sum, comma, CO. And then we have to close this with the AND module. Now here the type declaration. So that is input A, comma, B, comma, C in. And then output sum, comma, CO. Now what we have to do is, again, I am repeating, we can code it here in a different ways. We know the Boolean expression means do it in a Boolean expression, the data flow level modeling using the Boolean expression. So let's write the Boolean expression for this full adder. We know that sum is given by A XORed with the B, and that is XORed with the C in. In digital logic, we have studied this. And CO is A ampersand B, that is A ANDed with B, and then OR, you have to OR, and then A ANDed with the C in, and then again OR, and then you have to do B and with the C in. So this Boolean expression is what we are directly writing. So that is called data flow level modeling. For XOR, we know the operator is this. For AND, operator is the same. That is this one, ampersand. And for OR, we have this pipe or bar, vertical bar. Okay. So this is for OR. This is for XOR. And this is for AND. And in data flow, we use keyword assign. All right. So let's do that coding now. So here, assign sum equal to A XOR. That this symbol is called caret symbol. This one is a caret. This caret symbol. So that's how it is. A XORed with B, B XORed with C in. Then semicolon. Now assign CO equal to, again, this expression, exactly this expression we are going to write. Okay. So A ampersand B, and then this vertical bar or pipe, then A ampersand C in, and then again vertical bar B ampersand C in. Then terminate with a semicolon. So we have done with our full adder. So save this file, click on the save icon. So here, fa.v, save. Now open again another file, new, source, Verilog. So this time we are going to code here that 4-bit ripple carry adder, RCA, ripple carry adder. Now module RCA 4-bit, open the parenthesis. Inside that we have A, comma, B, comma, sum, comma, CU. Now the type declaration, input, and this is a vector. A is a 4-bit vector. So in Verilog, we do this way vector. There are various ways. Recommended is this approach. Like you can also have here, if you start with, let's say, -2, then -1, then 0, 1. So here the range you can have -2, colon, 1 also. But this leads to a lot of confusions later when we really want to make some, design. So, but this kind of approach, this is this approach, Little Indian approach. This approach, one can easily remember, like, this is the MSP side. So the moment when we tell this is a 4-bit, then anyone can guess whatever the variable is here. So then A of 3 is our MSB, A of 0 is our LSB, like that. But some other, ranges, if you prefer, this indexes, if you prefer, then that leads to confusion. So the recommended is this, that is Little Indian approach is recommended. Okay, this approach is called Little Indian approach. So now the size is 4-bit, so that is for A and also applicable for B. Now the output here is output here. Output size is sum is of 4 bit. Sum is of 4 bits. That is sum, and we will have one carry out. So that is for carry out CO. Now we only have to instantiate those full adders. As I said earlier, part 1 also you can check. So I told that in this big, box, inside you have 4 full adders. This in part 1 I have covered. In this also in the introduction part I took out. So let's do that way. So first, let's copy this one here. Just copy this and paste it here 4 times. 1, 2, 3, 4. And give the instantiation name ins1. What is the instantiation name? I have already covered in my previous videos. Please check them. ins2. And then this is ins3. And then this is ins4. This properly we have to pass here, this inputs here. So if you look at this one, what we are passing to this one first, A of 0, B of 0, right? And this Cn is not there, this is 0. So what comes is we are tying it to sum of 0. And then this is intermediate signal, that is we are calling it as C1. So let's try properly, that is A of 0 and then B of 0. And then this Cn is not there. So that is 1. Tick, this is spelled as tick, that is single quote. B, then 0. It means 1 bit 0, like that. This is sum of 0 we are binding. And this is not CO, actual. CO is last. The last block will give this actual CO. But intermediate, these are C1. From here it is C2. From here it is C3. So let's call here C1. Now the second instance, A of 1, B of 1, and this is C1 we are binding. And this is sum of 1. And this is C2. And then this one is A of 2. And this is B of 2. And this is C2. This one is C2. And this one is sum of 2. And this is C3. Now finally, A of 3, B of 3, and this is C3. And this is sum of 3. And this is CO. Because as I said, this is the last block, right? That is our CO. So makes sense? Okay. So now I have done with all of these connections. So now this module needs to be enclosed with the AND module. So you have to save this file, save, and give proper name, relevant name, that is RCA4bit.v. So .v you don't remove, the only title you are editing, okay? So save this file. Now, if you look at this project here, this project window, we do not have any files here. We have to add the files here. So right click, add to project, existing file, browse. It will take you automatically to the folder where you are working. There select this .v files. Then open. Then click OK. So now your file's been added to the project. So now you just compile this one. But before we do that compilation, we have to write the test bench, right? So this test bench, let's write very quickly the test bench. Go to this file, go to new, go to source, go to Verilog. Here, backport, time scale, 1ns/1ps. About this, I already spoken in my previous videos. Module, TB, The T stands for test, B stands for bench. Test bench underscore, what is that you are testing? RCA 4-bit module, right? So give the same name, underscore, then the same thing. Now go to this RCA 4-bit, copy this input and output variables, copy them and paste them here and change this input to reg. This also I've spoken in previous videos. Reg is a data type which will have the property of holding the values. So we are giving different values for this AB, right? It should hold them. It should store them. So for that, reg data type is suitable. Sum is the output, so that is a wire. That must be wire, not reg. That must be wire. And CO also output, so that also wire. So now you have to instantiate the module that you are going to test. So we are going to test this module. Let's call this module. Copy this module name till this semicolon. Copy and paste it here. And give the space here. Call it as a DUT, design under test. Now here, this initial, then begin. This begin requires end, and given that module is end module. So later we may forget. So now only I'm just skipping. Now what is required here is a different intervals. I have to apply this AB and ensure that I'm getting proper sum and CO. So what I have to do here? So I'll be making use of this, as I said in the part 1, this dollar $u random, unsigned random integers. It will be generating this system function. So, and then I'll be taking the modulus of that by 16. So if I do that way, then the remainder I am actually going to capture here. So that remainder will be between 0 to 50. If I do this way. So let me demonstrate how I am using. If you have regarding this any doubt, you please reach me out or comment there. I will respond. So now let us do that. But how many times I wanted to do? I wanted to do for 10 values of A, 10 values of B. So I'll make use of this repeat loop. Repeat, repeat, 10. So I'll be writing multiple statements under repeat loop. So I need begin and end. So those multiple statements are A equal to dollar $u random. And I have to keep that inside the parenthesis. And then modulus, then 16, then semicolon. Copy this entire thing, Control C, and paste it here, Control V. Change this A to B. And here, this is modulus 16. Modulus 16. And then give some delay. Hash file delay. So this is because at zero simulation time, you are applying this very beginning. After that, 5 time unit delay. 0, at that, this AB been applied. After that, 5 time unit delay. Then loop will be, continuing till this count is 0. Then after again 5 delay. So like that. So that's why this delay is required. So now, here to print here in the console, in the past video I demonstrated. So you have to put here dollar monitor, and inside this, what is that you wanted to print? So I wanted to print here simulation time at the rate time, and the format specifier is percentage G. NS is for my reference, that is in nanoseconds. A, I wanted to display in binary. B also I wanted to display in binary. And then CO, that is carry out in binary, and sum also in binary format. Now I just copy this, copy, and after double quotes, comma, then paste it here. Just change this one because CO is here, the sum is here, right? So that order must be followed. So here CO. So now this is for printing in the console, this dollar monitor. If you don't put this dollar monitor, then in the waveform window only you have to see the output. Once this loop is done, when I come out here, then I'm taking hash 5, that is further 5 time unit delay, then dollar stop. The dollar stop is the system task to stop the simulation. Okay. So now save it. Appropriate name you have to give. That appropriate name is TB underscore RCA 4 bit. And this dot V, you do not disturb this dot V. Okay. Save it. Now, this test bench needs to be added here to the project here. So right click, add to project, existing file, browse this test bench file, select, open it, and then click OK. So that this test bench also been added. Now go to compile, compile all. So it is saying some error here. So let's check how to check this error. You have to double click this one. It will open up like this, and it is showing which file here. This is TB underscore RCA 4bit.v. And this 13 is line number 13. There something it is saying missing argument. So here some missing argument. This percentage G we wrote it down, right? For that there is no corresponding argument here. So that argument comes here with a dollar time. Dollar time is a system function. It returns the simulation time. So for A, we have this. For B, we have this B. For CO, we have. For sum, we have. Okay, save this one. Again, go to compile, compile all. Now, no errors. All right. So now what you have to do? Simulate. Start simulation. Now here work folder, you expand this plus sign. Select your test bench module name. Click OK. Now, if you want to see in waveform, you can right click here, this under sim default, this TB underscore RCA 4-bit you can select. Now currently here, if you see, just a minute, I have to arrange this. Arrange now. Windows, 1 minute. Complete set. Okay, so now if you look at this, let me close this one. This window is not having any variables now currently. So now if I add here by going to, this sim, see the tabs here. This is sim is of a simulation. So right click here, add way. So now they've been added here. So now if you, now here in the console, so far nothing is there here, that is output. Now here we have to click run. Before clicking run here, this PS, let's change to NS, that is nanoseconds. So now click run. So now in the waveform also you can see here how to see all of the values here. In the past videos I have covered. Just click here, see for these icons, there is a one icon zoom full. Click on that zoom full. So now you can see all of the values. And here in the console also you can see. So you take these values and add and see what is the result that you are going to get. So in case here, if you look at this example, we have 1010. So this is, we have 1010. And another operand also 1010. Now, if you add this 0, this is 0, and carry out, this is 1, and this one is 0 and carry out. So see the result here. 0100, 0100 is sum, and carry out is 1. So that's how you have to work out for the other here shown results. And that's how in external exam also you have to justify. Simply don't say something I got, sir. Don't say like that. Select the click here corresponding to this time interval. Here are the values. Work them out and justify that this result is correct. Okay. So kindly practice this. Pause the video. See the code. Practice in the tool. If any issues, please reach me out on my phone. Do not drop the WhatsApp message. Okay. So how to close this simulation? Go to simulate and simulation. Then click on yes. So that way you will not be closing your actual application. Only you are closing the simulation. Okay. All right. Thank you.